everyone. My name is Khushi Jaiswal from CAC Section A2. I'm from Ramdev Baba University, and today, as a part of my teacher assessment for Introduction to Quantum Computing, I will be presenting on the topic spin operators, observables, expectation value, and variance. These four concepts are the mathematical backbone of how we measure and understand quantum systems. By the end of this presentation, I will be explaining what spin actually is, how we predict measurement outcomes using expectation value, and how we are going to measure certainty using variance. So let's start with the most fundamental question. What is spin? In classical mechanics, we think of spinning top or planet rotating on its axis. But in quantum mechanics, spin is not physical spinning. An electron in a point particle. It doesn't have surface to spin. Instead, spin is an intrinsic form of angular momentum. It is built-in property just like mass or charge. For us, a computer science student, the most important system is spin particle like electron and many protons. It has two possible states. First, spin up, which corresponds to the state 0k or logical 0. Then spin down, which corresponds to state k to 1 or logical 1. This is exactly how physical qubits are realized in hardware. Before we look at a specific spin equation, we need to understand what an operator is in quantum mechanics. The best way to understand this is through a linear algebra. A quantum state is a vector. Operators are the verbs of quantum mechanics. They do things to qubits like rotating them or flipping them. So spin operators are derived from Pauli matrices and they determine the measurement outcomes. Now we have learned what is operator. So now we are going to learn what is Pauli spin operator now. So specifically for spin, we use a set of operators which called as polyspin operators. These are critical because they correspond to the measurement along the x, y, and z axis. Like, and the total spin operator S vector is related to polymatrice sigma by the formula x vector h cross by 2 sigma vector. The first gate we have going to see is poly X gate, which is Sx equals to h cross by 2 in matrix 0, 1, 1, 0, which is we have also denoted by sigma x. Then our next gate is poly Y gate. Its value is corresponds to sigma y h cross by 2, 0 iota minus iota and 0. Then our last poly gate, it is poly Z gate. So poly Z gate measures the spin of the qubit along the Z axis. And this is the phase flip operator and is used to measure the standard basis. So basically, it gives the two fixed results, which is upspin, which is h cross by 2, and downspin minus h cross by 2. So now we are going to tell that S cap x and x cap y are not commute. So what is x cap? It is h cross by 2, 0, 1, 1, 0 matrix. Then xy cap is h cross by 2, 0 iota minus iota 0 matrix. And for further use, we will be writing xz cap, which is s cross by 2, 1, 0, 0 minus 1 matrix. So when do we say that two matrices are commute? When x, z cap and x, y cap equals to 0. When they are commute. So first we will assume that they are commute. Okay. Then what is x, sx, comma xy? This is equal to xx minus sy, xy into xx, sx. So here we will put the value which we have put here as x, h cross by 2, 0, 1, 1, 0 into h cross by 2, sy, h cross by 0 iota minus iota 0 minus h cross by 2, 0 iota minus iota 0 into h cross by 2, 0, 1, 1, 0. Now we have to do matrix multiplication, like it will be like this row and this column. So here h cross by 2 whole square will be common. Now we will do matrix multiplication. 0 into 0 will be 0 plus 1 into iota will be iota. Then 0 into minus iota will be 0 and 1 into 0 will all be 0. Then 1 into 0, 0 and 0 into iota will also be 0. So here it will 0. 1 into minus iota. 0 into 0, 0. Here our first matrix is done. Now second matrix is same method like this row and this column. 0 into 0, 0. 1 minus iota into 1, it is minus iota. 0 into 1, it is 0 and minus iota into 0, 0. So here it will be 0. Iota into 0, 0. And 0 into 1, 0. Then iota into 1, it is iota plus 0 into 0, 0. So second matrix is also done. So h cross square upon 4 whole matrix iota 0, 0 minus iota minus iota 0, 0 and here iota will be there. Now we have to subtract the matrices. It would be very simple method. So iota into minus iota. It would be minus into minus iota. Then 0 minus 0, 0. 0 minus 0, 0. Minus iota, minus iota. Minus iota, minus iota. So it would be h cross by 4, 2 iota, 0, 0, minus 2 iota. As here minus into minus will be plus. Now we will take 2 and iota common. So it would be h cross by 4 into 2 iota, which we have taken common. It would be iota 0, 0 and minus 1. 1, 0, 0, minus 1. As iota we have taken common. So we will divide, it would be h cross by 2 now. And h cross by 2 by 2 into iota 1, 0, 0, minus 1. Now we will take h cross and iota common, and here h cross by 2, 1, 0, 0, minus 1. It is equivalent to s cap set. So now s x comma sy, it would be equal to h cross iota into s cap set. And here we have proved that no, sx and sy are not commute to each other. So here similarly, we would say Sy comma Sz would be equal to iota h cross Sx. We will take it in clockwise manner. Then Sx comma Sx would be iota h cross Sy. Then if we reverse it like Sz comma Sy, it would be minus iota h cross Sx. Same like this. And same like this, it would be Sx Sz equals to minus iota h cross Sy. So our conclusion is that for commutative condition is two matrices are said to be commute if their commutator is zero, which is like A cap comma B cap equals to A cap B cap minus B cap A cap equals to zero. But in this case, Sx cap comma Sy cap is not equal to zero. Hence, we have proved. So this brings us to the concept of observables. In classical physics, we just measure the things, but in quantum mechanics, every physical quantity that can be measured, like momentum, energy, or spin, is called observable. Every observable is represented by Hermitian operator. Now, why Hermitian operator? Because Hermitian matrices always have a real eigenvalues. Since we can only measure real numbers like energy or spin direction in lab, our operator must be Hermitian. So when we measure an observable, the quantum state collapse into one eigenstate of that operator. And spin operators are the observables. Now, how do we predict the result of a measurement? We use expectation value. The expectation value denoted by bracket A is not the result of the single measurement. It is the statistical average of many measurements performed on identical systems. In quantum computing, we call this shorts. If we run a circuit 1,000 times, the expectation value tells us the average output. So the formula goes like this. Bracket A, it would be psi bra psi into operator A and Kate psi. So basically we read that psi bra operator A psi Kate, right? Here we can find the value of expectation value, which is probability into value of the system. In before, we have seen what is expectation value. So it is a probability of X value of measurement. So it is most likely the value of measurement. And so now we are going to find how to find expectation value. Suppose we have thrown a dice. So what is the expectation value of dice? It would be, we denote expectation value with this brackets, okay, equals to 1 by 6 times value of the system, which is 1 for 1, then plus 1 by 6 into 2 plus 1 by 6 into 3 till 1 by 6 into 6. So here, what is 1 by 6? It is the probability of having 1 in in the dice. Probability of having 1 in the dice. And 1, it is our value of the system, right? And here D is expectation value of dice. And it would be around 3.5. Yeah. Now, now suppose our electron is spinning in up state, state 0, where we take vector 1, 0. Let's find the expectation value of the spin along the z direction, which is sz gate.
So, before we have learned what are operators. So, there are many operators for like spin, momentum, and etc. Now, let's take an example for operator A. How do we write the expectation value for operator A? So, bracket A equals to bra psi, operator A, Kate psi. And as we know that bra psi equals to Kate psi dragger. So basically we operates operator A on Kate psi and then we do Kate psi dragger and operate it on operator A. And the way now we have written it is like the probability, we are finding the probability basically, which is psi square. From we have taken this from the Schrodinger. So for what does the Schrodinger say? That integration psi into psi star dx equals to 1. So we can also write expectation value of A equals to integration psi of operator A psi star dx. Now we are going to find the expectation value for spin operator Sz. So first we will write how the notation are done. Sz, bra 0, Sz operator, Kate 0. And we know bra 0, Kate 0 is 1 0 and bra 0 is Kate 0's dragger, right? So first we have written what is Sz, h cross by 2, 1 0 0 minus 1. If we multiply h cross by 2 with the matrix, we get h cross by 2 0 0 minus h cross by 2. Then if Sz is operated on Kate 0, then our answer would become h cross by 2 Kate 0. And if we taken the multiplication of bra 0 with the sz vector operated on Kate 0, our answer would be h cross by 2, right? So basically our answer came to be sz, expectation value of sz is h cross by 2.
So, why do we need a quantum gate many times, which is 1024 shots? In real quantum computer, a single measurement is not reliable because it has noise, quantum randomness, and hardware error, too much errors. To correct the final answer, we repeat the measurement as many times we want. So, for example, 1024 measurements will be equivalent to 1024 shots. If we have seen the expectation value, which tells us about what is the measurement or the result of the measurement, the variance tells us that the result is fluctuating or not. So it tells us the uncertainty or the spread of the measurement result. So the formula goes like this: variance equals to bracket operator E square minus in bracket expectation value whole square. So here is the key takeaway. If we are using Z gate operator SZ on the state that is already on eigenstate like gate 0, the variance becomes 0. Let's see how. So the summary tells like this means there is no fluctuation. If we run the quantum gate 1024 times, we get the exact same result every single time. However, if the state was in superposition, the variance would be the non-zero, indicating the randomness in the output.
Now, if we talk about the variance, let's take two examples of dataset. In first dataset, we will take the first one digit and very small numbers like 2, 3, 4, 5. That's it. And for second set, we will going to take 7, 5, 2, 10, 11, 15, two digit number or very big numbers. So we are going to use normal distribution table for the variance. Now for the dataset 1, the normal distribution table for a curve is very less dispersed, means the width of the curve is very less. But if we see in the many means large data sets, the variance is fluctuated and become very big. So if we have more bigger numbers or the data sets differ, the variance differs also. So for this, variance is more dispersed, and for this first data set the variance is less dispersed. Now let us take an example for like 100 or 1000 readings. The set, if we take the data set as unbiased, now we have to find the average data point. So the normal distribution table, we are going to make the curve and the point where it touches the 0, that is the average data point, and the highest point, we can also say the amplitude, but it's not an amplitude, it is the highest point of the curve is known as average data point. That means many of the data sets are coming in between, like from this to this, we can say this area covers only the points where it which is less than 100, and the point of this is where from 100 to 900 points or readings are coming, means many much our readings are coming in this area, and the leftover area which is from here to here, we can say that from above 900 to 1000 or more than 1000 also the area comes. Now we know that for 1 sigma, 1.5 sigma and 2 sigma, the data is 67% for 1 sigma, and for 1.5 sigma it is 87% of data, and for 2 sigma it is 96% of data. Now what is sigma and what is 1.5 and 2? So basically sigma is the standard deviation, and why we are saying 1, 1.5 and 2, it is the standardized way we can understand. Now here in this curve you can see that this is a normal curve, normal distribution curve, and from the area this much, we can say that this from here it is 1 sigma, and this area covers 67% of the data set, right? Then comes a 1.5 sigma, we can see that from here to here it is total 1.5 sigma, and which covers our 87% of data set. Now the last 2 sigma, it comes under very much data sets, or we can say that many data sets comes under 2 sigma. From here to here it is 2 sigma. You can see the colored shaded region, that is 2 sigma. Now how do we find the variance? Variance is sigma square and bracket sz square minus expectation value square. Let us find the variance of SZ cap, or we can say Z gate. And first we have find SZ square from multiplying SZ into SZ. The answer comes H cross square by 4 1001, and if we multiply H cross square by 4 with the matrix, it comes H cross square by 4 0 0 H cross square by 4. Now to find SZ square bracket, it comes under bra 0 SZ square kate 0. As well, we know bra 0 equals to kate 0's dagger, and SZ square operated on kate 0, it comes to be H cross square by 4. And then if we take bra SZ square kate 0, it comes to be H cross by 4. Now before we have find the expectation value, and now we have find also bracket SZ square. So we are going to put the values for sigma square. Here it is sigma square h cross square by 4 minus h cross by 2 का whole square. Here sigma comes to be 0. Sigma square comes to be 0. Why? So it means that if we take the z gate and for 1024 times we are running the quantum gate, the variance shows no fluctuation for the randomness in the measurement of electron.
So now let's take a very short question where we have to find expectation value and variance for the operator ohm. Now operator ohm is given like matrix 1 iota minus iota and 2, right? So for as we know that for quantum state it would be like the variance would be psi square minus psi whole square. So for we know that for operator it would be, so for operator the variance would be ohm square minus ohm square. So now let's take a very quick question for finding the expectation value and the variance of ohm operator. So we have given the ohm operator and Kate psi. Now we just have to find bra psi also, which is dagger of Kate psi. So what is dagger basically? It is conjugate transpose of the Kate psi. So it first we are going to transpose it is p root 2 by 2 and root 2 by 2 iota. Now conjugate it becomes minus, which basically the bra psi is this. Now for expectation value we are going to need the ohm operator, which would we will like write like bra psi ohm operator Kate psi, and that's how we are going to find the expectation value for this. So first ohm vector on operated on kth side would be 1 iota minus iota 2 and root 2 by 2 and root 2 by 2 iota. It would be 2 by root 2 as it is 1 by root 2 and 1 by root 2. So it would be 2 by root 2 and 3 iota by root 2. Now for brass side, we are going to put and multiply with ohm vector with kth side. It would be 1 by root 2 comma minus iota by root 2 into 2 by root 2, 3 iota by root 2. So our answer would be 1 by root 2 into 2 by root 2 plus minus iota by root 2 into 3 by root 2 iota. So it would be 2 by 2 plus, as minus is given, so we will going to take minus and iota squared 3 by 2, right? Since we know that iota square equals to minus 1, then 2 by 2 minus into minus 1 into 3 by 2. So here minus minus becomes plus, so 2 by 2 plus 3 by 2, which is 5 by 2, which is 2.5. So our expectation value, which is ohm vector, is 2.5. Now let's find the variance for ohm vector. And we know that sigma square equals to ohm square minus ohm expectation value ka whole square. So first we are going to find, the ohm square, which is ohm in vector into ohm vector. 1 iota minus iota 2, 1 iota minus iota 2, which is 1 into 1 minus iota into iota, just here would be 2, then 1 into minus iota into 2, it is minus 2 iota means minus 3 iota. Here 1 into iota, it is iota into 2 into iota, which is 3 iota. So 3 iota. And iota into minus iota, it is minus into minus 1, 1 plus 2 into 4. 2 into 4 plus 1, 5. Now we are going to operate ohm square with psi kth, right? So yeah, we are going to also write psi square bra equals to bra psi ohm square vector into kth side. That is how we are going to operate it on first kth side. So 2, 3 iota minus 3 iota and 5 operated with 1 by root 2, 1 by root 2 iota. It would be 5 by root 2 and 8 iota by root 2. Right? Now operating brass psi on ohm square side. As we have find here, brass psi is nothing but 1 by root 2, 1 by root 2 iota minus, and which is multiplied by 5 by root 2, 8 iota by root 2. So simply we are going to multiply and add. So it would be 5 by 2 plus minus iota into iota, which would be minus iota square, which will be once again, upon into h by 2. Let's not cross it. First we will add. So 5 plus 8 would be 13 by 2, which would be 6.5. So basically our ohm square is nothing but 6.5. Now for variance, which is sigma square, it would be bra ohm square minus bra ohm. Here bra ohm square we have find 6.5, and here we have find the expectation value, which is 2.5. So 2.5 whole square, it would be 6.5 minus 6.25, which would be 0.25. So sigma square is nothing but 0.25. Now expectation value is equal to 2.5, and sigma square, which is variance, is equal to 0.25. Hence, we have solved the question. Now, finally, let's discuss why this concept matter in the real life. We can categorize the application into computing, medical science, and security. So, qubits in quantum computing, spin particles are the physical realization of qubits, and here we directly in medical science we use magnetic resonance imaging relies entirely on spin of protons in your body. The machine uses magnetic fields to align spins. The expectation value of the collective spin is what generates the signal to create clear image. Then we have scientific researches where we also use electron spin resonance, ESR for drug discovery, and atomic clocks for GPS synchronization. So, from diagnosing diseases with MIR to security data with quantum cryptography, Spain and its operators are at the core of modern technology. So, to summarize my presentation, first point, spin is an intrinsic quantum property. Then spin operators determine the result. Operators acts on states and poly operators are specific for spins, right? And observables are measurable physical quantities, and the expectation value gives us the average result. Then the variance tells us the uncertainty in the measurement, and for zero variance means perfect certainty. And that's how my presentation would I would like to conclude. Thank you for your attention.